I forgot. Can you hear it now? Yes. Okay. Thank you. So we said that the highest order term is the most important because those terms, oh, I forgot one term. Without any derivative, when you bound the insoluble space Hm, it will just bounded by absolute constant times the Hm norm. So it will be absorbed by the good terms, and those we call it Mu. And this we called it Ms. Yesterday we treat one of the Mu, which is the first term, y plus u bar dot gradient u tilde. So I'll write down the conclusion here. Let's give it the negative sign. And doing the L2 inner product, this will equal to our two good terms, which is this. It's corresponding to the radial derivative. And plus angle derivative. And then plus something that is uniformly bounded in the homogeneous Hm norm and some lower order term. So lower order term can be bounded by a constant depends on m. So I would just forgot about the s. Those things will be dealt with by a concept of perturbation. So lower order term is just okay, and may gives the finite up to finite codimension instability. So if we have such kind of term, we just write it as lower order term to make our life easier. So this is the 1.1, the one that's concerning the y plus u bar dot gradient u tilde. And then we consider this, the first term in the ms tilde. So this is very similar. So I will skip all the proof because the only difference is just you change the u tilde by s tilde. So if you do the same estimate, it will be same. So just write down here. This one. Still, all the coefficients are same. It's just you change the u tilde by s. Okay, so now it's the mixing term. So the terms concerning the second terms in our Lu tilde and the second terms in our Ls tilde. So they are mixing because the derivative is on S tilde in the term of U, and the derivative is on U tilde in the equation of S tilde. So the highest order term cannot be directly used integration by parts, but the cancellation is between the sum of them. So let's have 1.2. Or let's give it a name. So this is our 1, let's say. This is 2. This is 3, and this is 4. So let's work on 2. So still you will have 2 parts, right? The major parts, and also the one that you may give you the dissipativity. And then we do the integration by parts for the first part. So let's say 2.1. So this term is in the integration of the equation of S tilde. So when you do the integration, you do that. So no, this U tilde, sorry. So you cannot do anything yet because by itself you do integration by parts. This does not get cancellation, but it will be cancelled by other terms, like here, okay, this divergence U, and the sum of them will be a lower order term. So I will just leave it like that. Oh, sorry. Plus the lower order derivative. And then the second one, 2.2. So we consider this negative alpha n. Still, you want to time the gradient U tilde. So now we again do a similar thing that we did last time. We want to write down the sum as the gradient n-1 derivative and 1 extra derivative to see how the structure is look like. So summation, our gamma prime, and we'll have an alpha derivative and have an I derivative. So this, let's say we put alpha derivatives in U tilde, and then we have partial gamma and partial I S tilde, and in front will be a partial alpha S bar. Because this is UI, because U is a velocity. And this partial R, partial gamma is the mth order derivative, and you distribute 1 alpha into the S bar, and this partial I is originally there because it's the S gradient S tilde, and it's corresponding to the ith term of U. Okay, so it has this mixing facts. So now how do you combining them together? So I still use the fact that this S bar is radially symmetric. So we have this partial R S bar is equal to the S prime R times Y alpha over R. So plugging this into the equation, we have negative M alpha summation S prime partial I partial gamma prime S tilde Y alpha over R partial gamma prime. Okay. So again, this thing gives you an R derivative, and we can eliminate a sum with respect to R to alpha. this is negative MR. So now we'll be able to bound the whole thing. You just use the trivial L infinity non-bound. So bounded by M alpha and summation. Let's do this. They put L2 here and L infinity here. No, not L infinity, it's just use the absolute value to bound it. And you have a 1/2 from the Kurdish ones. So then you get the gradient, MR. There's no sum, put everything in the gradient. So here we just use this loose bound to use the gradient to bound everything, no matter the radial and angle. Okay, so that's the bound that you have. So this is 2.2 and this 2.1. So this will give the estimate of these two and put them together. This will be our estimate for term 2. So I will write it down. So gradient M negative alpha S bar gradient S tilde times the gradient M U tilde. This will gives you a term that we haven't treated, which will be done by integration by parts. And then we'll have the term that can be bounded, which will be absorbed into the other term. Plus lower order term, so those are good. So this is our second term. So what about the last one? The last one is very similar, it's term 4. So we'll do it in a similar way. So the term 4 involves the gradient mth derivative of the alpha S bar divergence. Still, we have a highest order term, a term that in the exact same order. And then other terms that are low order. So the highest order term will be cancelled from integration by parts with the term in the term 2. So let's see. So negative 4. And times another term, which in our case is the gradient ms tilde. So this is cancelled with this. So they are the gradient of the gradient ms tilde times the gradient m of u tilde. And then can be done. And then the 4.2. The 4.2 will also give you a bounded term in a similar way, but there's a slightly difference, as you will see now. So now I still use summation into the gamma prime and summation into the alpha derivative and I derivative. Okay. So the alpha derivative is on S bar because you distribute one here, and the divergence is the I. So partial I, partial gamma prime, UI. And the gradient S tilde is partial alpha, partial gamma prime, S tilde. So the combination of those parameters looking like this. So still, we want to rewrite this as the radial parts because it's radially symmetric. So this gives you negative M alpha. Prime Y alpha over R, partial I, partial gamma prime. So now this still the Y alpha over R is combined with this and give you a radial derivative. All right, here. Hopefully I'll get enough space. So this can be bounded similarly as before, but you don't want to do it straightforward, because if you're straightforward, this divergence will give you a parameter, the constant loss, probably connected to dimension, and we don't want that. So just do the integration by parts twice, put the I derivative here and R derivative here, and then go back to the same thing as before. And all the errors coming from the integration by parts are just lower terms, which are good. So this is actually like this. Partial gamma prime u to the I, partial gamma prime S. Okay. Plus the OM of the gradient M u tilde. Times the lower term. So we have such kind of integration by parts bonds, and so this OM can be distributed into this part, right? One, so it can put a small constant in this gradient M and a large constant in the lower term, so everything will be fine for these error terms. Okay. So then we have all those things, and this is exactly same as the thing that we got from the 2.2. So we use the same bound to bound it. Well, right here. So our term 4 is look like this. So the gradient M, relative alpha S bar divergence U tilde, gradient M S tilde. This is also less than or equal to 1/2 M alpha, partial alpha on S primer, times the gradient M U tilde square plus the gradient M S tilde square plus lower order term minus this highest order derivative. Oh. So now things are clear. So just sum all those things. This is 4, and this is 2, and this is 1, and this is 3. So find that for this 4 and 2, these are just fold gradients instead of radial derivative and angle derivative, but you split this into radial and angle. So the coefficient in this bracket and this bracket will be changed a little bit. So summing this up, you will have the full energy estimates for the linear right operator. So it's gradient M mu tilde, gradient M mu tilde, plus the gradient M S tilde, gradient M S tilde. This will equal to negative M, or less than equal to negative M, 1 plus U R prime minus alpha partial R S1 times the radial part plus the angle part. So that's what you get, and others are lower order term. So when the M are sufficiently large, this gives you dissipativity. So as long as this is positive, and those are positivity conditions satisfied by the profile, the self-singular solutions. So that's the proof for the linearized operator energy estimate. Any question? Yes. Yes. What do you mean by the best?
Like, I guess you have condition like 1 plus UR5 minus alpha TRS has to be bigger than 0.
Yes, it will be bigger than a constant. That's well, this is not exact sharp, like there's no weight. So if you put different weight, you will gain a little bit for this compressible Euler case. So this is in the paper of Jiajie, COD, Scholar, and Rico, they put weight. And because they are in 2D, this condition doesn't satisfy the profile in the whole space. So outside of a critical zone, they put a weight and to compensate this. So if you have a weight, basically, it will come from the integration by parts, right? If you, let's say, we do this, plus 1. And you have some weight, so basically, you will give negative gradient M mu tilde square and the gradient phi. So if phi is chosen depending on M and sufficiently good, it may give you some term that will absorb these things. But the tricky thing is you cannot put weight whenever this coefficient in front is 0. So in the sonic point, there's no weight can be done. So at least near sonic points, you should have these repositivity conditions. Yeah, because if you put weight and there's a coefficient that's vanishing, it will be very bad. Yeah. And this is one thing, but so this is for the compressible Euler, right? If you go to the Schrodinger, and we mentioned at the beginning, then the Schrodinger case, you cannot put weight in the highest energy level. This will lead to the derivative loss. So you just imagine such kind of equation. So we have Schrödinger, partial Tu is I plus U plus nonlinearity. So this, if you don't put weight in Sobolev space, this will be cancelled. There's no derivative loss because you have a imaginary number I in front. But once you have a weight, then you cannot close it in the Sobolev energy estimate. So you do this, let's say L2, but put a weight. So the first term, the second term will be good because there's no derivative, but the second term, oh, sorry, this is complex. I cannot write it in this way. So it should be the real part of this times conjugate. So when you distribute this into this part, it's still fine. But if you distribute this gradient Laplace into phi, this will give you a derivative loss. You cannot close. So whenever I put the weight into the Schrödinger, it's not good. So this. Over phi. So this cannot be bounded in L2. So that's the difference of Schrödinger and compressible Euler. Yeah, but in a Schrödinger case, the profile these we use, they satisfy this globally, so there's no issue here. But if there's issue there, we don't know how to treat that. Like there's no way it can be done. So yeah. Okay, thank you. Okay, so let's go to the nonlinear. So for this kind of problem, actually nonlinear is much better than the linear, as you will see later, because the nonlinearity just have the exponential decay term times exponential decay term. So nonlinearity. Nonlinear stability. So first, let's write down the original equation because we are going to use an estimate for that. This is negative. Let's write away. And now we just write down the NU and NS. So they are all quadratic. So first we write down the arguments for the linearized operator, then we'll apply this on this whole equation, use the Duhamel's formula and the bootstrap arguments. So the bootstrap is not exactly same as the paper to avoid some technical details. But the idea is you want to have a low order derivative term that is give you decay, exponential decay, and you have a boundedness arguments in the higher order derivative. And then anything in the middle, they are interpolation. But the good thing about higher order derivative is that you don't need to have a decay, you just need to have a very large bound. So we'll use this as a finite dimensional stability for the linearized operator. So now you have the X, which you can think of it as a with HM space with M very large. So they are split into the two invariant subspace, which are stable and unstable. And on the unstable space, there exists a metric B. They are finite dimension, so you find equivalent metric such that the norm will growth. So the L is just the combination of LU and LS. So it grows at a certain rate. So because our spectral gap from the energy estimate and also the maximality. And on the stable space, we have exponential decay. Yes. So we will use this to apply our nonlinear estimate. Okay, so let's do the bootstrap arguments and all those estimates. So first we want to give a sequence of parameters that we want to use to bootstrap. So there include several small parameters and several large parameters. So first, the delta G is something between 0 and 1. Actually can be chosen to be other things if you only have compressible Euler, but let's fix it to be 0 and 1. And the time is S0. The starting point of the time is very large. So this is very small. And the delta naught and delta 1 is to control the smallness of the solution. They are satisfy such corresponding relation. The delta 1 is much smaller than delta 0, but delta 0 to the 0 or 2 is much smaller than the delta 1. So this because you have some nonlinearity happening. You want to make sure there's a corresponding. So sometimes you have a slightly better bound, but the quadratic of the original one will slightly better than this one as well. So you will see in the later how this works. And then those are, the epsilon is the thing that the coefficient of exponential decay is slightly worse than the 1/2 of delta G, the linearized decay rate. Okay. So we first work on the stable mode, with the assumption that the unstable space is controlled, we have the following bootstrap arguments in the two space. Okay. So with assumption, the projection of the unstable space of our use X is less than or equal to delta 1 e to the negative epsilon s minus S0. We want to improve the bootstrap argument. So we'll keep this as assumption for now and improve this too. So first is the X estimate. It is exponential decay with the rate epsilon and times theta naught. And the second is the estimate, but in the very high order derivative. But now this is not for the perturbation, it's just for the whole thing. The homogeneous HK is less than or equal to a bound E that is very large. So let's specify what's the relation of the K and the E. So the K and E, they are here. So the delta naught is always less than 1 over E. And it's less than 1 over K. And less than actually. So we just put things here. So basically, we choose sufficiently large order derivative, and then the bound will be very large compared to that. But the initial data and the bootstrap smallness arguments will also be very small compared to the 1 over E. So any interpolation will give you a decay, give you a smallest number rather than a large number. So that's how this parameter is chosen. So now let's do the first one. Oh, I shouldn't erase that. Oh, let's see. As long as I have this, I should be fine. So how do we do this? So we first want to control the unstable mode. So sorry, the stable mode, because unstable mode with assumption is good. So we just project it into the stable space. So partial S P stable tilde S tilde. So because it is invariant subspace, so you change this L and this the order of the projection and operator, and then you have the unstable, the nonlinear operator, the NUNS. And then the standard thing to do is to use the Duhamel formula. So the P stable, like evaluate at time S, is our operator. It's linearized operator. Let's call it TL. P stable. With the initial data, well, initial data of course will be chosen very small, plus the integral from S0 to S TL, and tau minus this is S minus tau, and P stable, and U tilde S tilde, tau. So this is our standard bootstrap arguments. So from the linearized operator, you already know the first bound. The P stable, X is less than or equal to the E to the negative delta G over 2 S minus S0 times the initial bound. I will just use U tilde S tilde, X S0. We can choose this sufficiently small. Let's say this is less than or equal to delta 1. And the second bound. So this you still use that, but now the range is not from S0 to S, it's from tau to S. So then we drop this unstable, we directly bound this. nonlinear term in X and do the integration. So the first is good because it's just linearized operator, and the second is good because you have the interpolation with the higher order derivative norm. Notice that the nonlinear term, you have some decay, some derivative loss. You have one extra derivative, and if you bound it in the sublift HM norm, then you actually have n+1 derivative. So that's why the whole thing needs a higher order upper bound estimates. But because it's quadratic, you don't really need a decay for this upper bound estimate. You just need a bound, and this bound will be absorbed by the smallness in the quadratic term. So let's write down this thing in details. So the nonlinear term, we just use a very loose argument. Let's say this is less than or equal to the gradient of u tilde hm plus s tilde hm times the n+1. And the first one, the bootstrap bound gives you the delta naught exponential decay. And the second one is the interpolation. So you basically have something like this. So delta 1 e to the negative epsilon s minus s naught to the theta 1 times e to the theta 2. Interpolate between the HM norm, which is x norm, and the HK norm. And moreover, the theta 1 is very close to 0. Sorry, very close to 1 because you are just one extra derivative and k is very large. So now you basically have a delta square, a little bit less than delta 0 square and a little bit less than this e to the negative 2 epsilon estimates. So we write down what we get. So this is less than or equal to delta naught 3/2, let's say, and e to the negative 3/2 s minus s naught. So then this can plug in into the original integral. This gives you P stable x is less than or equal to e to the negative delta g/2 s minus s naught, but times delta 1, this is the initial data, plus the integral from s naught to s1. And the bound e to the negative delta g/2 s minus tau, and delta naught 3/2 e to the negative 3/2 s minus s naught, tau minus s naught. So now you are in good shape because like from tau to s, you have the e to the negative delta g/2 decay, and from time from s naught to tau, your decay is e to the negative 3/2 epsilon. But the goal of decay is just e to the negative epsilon. So everything works out and you will have something like this. Maybe there's some constant, but it will not affect a lot. So e to the negative epsilon s minus s naught. So in the end, this will gives you bound because delta naught is very small and delta 1 is very much smaller than delta naught. So this will give you less than or equal to 1/2 of the bootstrap bound that you want. So this is the bootstrap bound for the first estimates. And well, let's give it a 1/2 or the, yeah, this is 1/2 and you plus the unstable assumption, then it will give you the full thing. So it's just 1/2 delta naught plus delta 1 and then it will be fine. Okay. So what we did is we assume this 3 thing. Well, and those 2 are bootstrap estimates and we improve the first one. So now we are going to improve the second one. And then this whole estimate is closed. And of course, in the end, we will deal with the unstable estimates. Let's forget about that. So let's improve the second one. Improve 2. So as you can see, it's also a energy estimate. The only thing difference it is in a very high derivative space. It's in homogeneous HK space. And you will figure out that it's actually not that different from the linearized argument, as you will see in this way. Okay. So first I erased that, so I want to write it again. Oh, sorry. So why it's not that difference from the linearized argument? So we can just split it into 2 parts. The first part is you just change this u to u bar, and then you will complement with another. You put another term with u tilde, but the first terms will just be the linearized operator. So separate into 2, and this is the linearized operator. But now it's just applied on u instead of u tilde. And this is linearized operator on s instead of s tilde. So this bound is just for free. And we only need to calculate that all the things coming from this leftovers are just bounded by a constant times the lower term. Okay. So let's recycle our linearized arguments. We still have here, so I will just write it down as here. Okay. So now you have this gradient k, Lu, gradient Ku, plus gradient KLS, gradient Ks. This will be equal to this negative k less than. There's no tilde because they are all U and S. the lower order term, well, let's just make things easier. It's capital O of E. Because interpolation is just even smaller, and this capital O doesn't depend on our K. So this well includes this, right? Because this is just LU and this is just LS. And now what about this one? Maybe let's call it EU or FU and FS. So this has still has derivative, but derivative is still okay. You can use integration by parts as usual to estimate that. And the only thing that may go wrong is that one derivative hit on U tilde and one derivative hit on S tilde. And this potentially have a K coefficient in front and will give you bad things. But from the bootstrap arguments, you already show that this one are very small. So they are very small times K, they are still very small. So they will not really change the coefficient a lot. So that's why they will not kill this K. So let's see how this works. Okay. So the board. This will not involve very complicated arguments as before. We just put them together. Of course, we have highest order term, but this is always integration by parts. U tilde grade K plus 1 U KU minus alpha S tilde. So those are just integration by parts, and it will give you the bounded terms, some capital O of E. And the second term is just the gradient K, gradient U tilde, KU minus alpha. So those four terms plus OE. So the first term is OE, and the second term is bounded by K times delta 1 times a constant, let's say, times e to the negative epsilon S minus S naught times homogeneous H1O. So it's still OE. Because this is very small. When the delta naught is chosen, it's very smaller than 1 over K. So this is capital OE. So now we put them together. You have this K large, and this is constant. This is greater than positive constant, and this is OE. So when K is very large, you put everything, you will get this thing. Partial S, gradient KU, gradient KU. plus S. This thing will less than or equal to K times a very small constant, let's say mu, times E of times itself. Plus OE. So this thing will not exceed this OE divided by K times mu. So this will give you presumably a better bootstrap arguments. So it's bounded by KE over K mu. Well, mu is absolute constant and K is very large. So the what? So these are the bootstrap arguments. Okay, so this is nonlinearity for this 1 and 2. So now what about the unstable mode? So we assume that the unstable mode is bound, then everything else is bounded. Well, the only thing that you need is the one way to do it is the topological arguments. And this is a very standard. Let's do it now. So now, because the unstable mode only has finite codimension, so you already eliminate the problems into the finite dimensional problem. So as long as this finite dimension things is controlled, everything else is controlled. Okay. Let's erase everything and write down the stable estimates. So what is the argument? So this is so of course not every initial data will give you a stability because the finite codimension stability. So the thing we need to show is for any initial data there exists a unstable something in the unstable space is fixed and then gives you the eventual stability results. Or if you want, you can restrict it to the stable space and then choose the unstable space. Let's continue. Call this assumption star. So this will eventually use a topological argument. So we want to show that the unstable space is bounded in a ball. So the way to show it is to show that on the boundary, if it's already on the boundary, then it will eventually immediately leave the ball. Then this will lead to a map from a ball to its boundary, and it's continuous. And this is identity on the boundary. And then, and then there's no fixed point. And then the fixed point argument will show that such thing doesn't exist. So let's first define the ball. So the ball is, let Ks to be this unstable thing. Us. So you have two balls. One ball is in our metric B. So this is just to fix some constants because there are different metrics. Even if it's in the finite codimension space, it's some constant difference. And another one is R tilde S. Want a slightly smaller bound in the original X norm such that it will always be in the second ball is always in the first ball. R tilde. Oh. There's R. So this will include two propositions. Well, first proposition is whenever the Ks is on the boundary, it will leave the ball immediately. So this one, the thing to use is our linearized arguments and the bootstrap assumptions. I don't have linearized. Write it again. So if you remember, the linearized arguments tells you the unstable modes, it's growing. So as long as you choose the ball is shrinking slower than the growing, it will leave it sufficiently fast. And you only need to bound the unstable as an error. So I will write down this linearized argument because we are going to use it here. So in unstable space, the LU part. So still you want to use the linearized argument and nonlinear, but now you project to the unstable space instead of the stable space. So partial S U tilde S tilde is equal to L U tilde S tilde plus nonlinear. Now the projection on stable space. So for the linearized operator, we use these arguments. This one will grow faster than it should be. So of course, the parameter is chosen such that the 6/10 delta G will be larger than the 4/3 epsilon. So partial S stable. B will be larger than 6/10 delta G. Give it square. Square minus the bound of the unstable space. So there's 2 and there's times 2. So we only need to bound the unstable space. And the unstable space, this will be bounded by that. Delta G. So by a constant of the norm bound in X times originally. So I just changed the B to X because it is just equivalent matrix with some constant. And then you directly drop this unstable space and to bound everything as a whole. And this is X. I think we bound this before. It will bound it by some interpolation of the 1 and 2. So I will just directly write that. So this gives you -12/10 delta G. So the only thing matters is this is quadratic. So this will be bounded by delta naught e to the negative epsilon s minus s naught times delta naught e to the negative epsilon s minus s naught times theta 1 times e theta 2. And the theta 1 is very close to 1. 1 minus theta 1 will be theta 2. And then times the unstable space. So, bound. So now you are at the boundary of the ball. So at the boundary of the ball, the norm is this delta 1 e to the negative 4/3 epsilon s minus s naught. So this thing is significantly smaller than that. So you just divide it by the boundary of the norm and you will get such bound. So So let's only consider the term 2 listed. So this part, let's say T2. So T2 is less than equal to the delta naught, let's say 5/6, a little bit slightly smaller. And then is less than equal to the delta naught 6/5 e to the negative 5/6 epsilon divided by the boundary delta 1 4/3 delta 0 4/3. Yes, just a total. E to the negative 3/4/3. Sorry, this is 1 plus 5/3, and this is 1 plus. Because it's quadratic, so you already have a 1. So the thing is, the delta 0, 1, 11/5 will be significantly smaller than delta 1 to the power 3 by our choice. And then this 11/6 will be larger than the 4/3. So this will give you a very small constant, which is less than equal to the, sorry. I should times this as the boundary. Less than equal to, let's say, 1/200 delta G times this. And then you're combining this with that, you get the partial S unstable mode is greater than equal to -12/10 delta G plus or minus minus 1/100 delta G times the norm squared. And such growth will be larger than the growth of the ball. So if it's larger than the growth of the ball, then it's exceeding the box immediately. So I would just say 12/10 delta G minus 1/200 delta G will be greater than equal to or smaller than 4/3 epsilon. And then you will have the everything. Yeah. So those in all those things, the quadratic is just heavily used. Like you have slightly loose when you have the interpolation because one derivative, but the thing is quadratic, so you will add something, and they are very small, and then everything will be controlled by the linearized estimate. So that's the logic of all those nonlinear stability arguments. Okay, so this is the proposition 1, right? You're already exceeding the ball, and then we have the final topological argument of proposition 2, and it will close all the bootstrap estimates with the assumption. No, justified assumption. So there exists specific initial data AS naught, which is in our ball, such that KS is in our smaller ball all the time. So now you already have proposition 1, like for any initial data, if it exceeds, it must leave the ball immediately if it hit on boundary. So let's say we can do it with the contradiction arguments. If no such initial data exists, then everything starting in the ball, it will finally going out of the ball. So there must be a time that it hit on the boundary. So this existing time will be smoothed by the local opposeness of the solution. So you can define a map, which is the point that it exists on the boundary of the ball. And this will be a smooth map. Sorry, the continuous map. So of course, this ball will change with respect to the size of the ball change with respect to time. So just renormalize a little bit and it will be a unit ball. So then there exists a map. From our RS naught to a boundary of unit ball, let's say. And it's defined as A to the B of A divided by the bound of the A. Yes. And then this will be a continuous. So this is, and then this gives you so you can also rescale the initial ball such that it is a unit ball. So this will gives you a continuous map that maps from ball to this boundary, and on the boundary it is an identity map. So from the fixed point argument, such mapping doesn't exist. So you close the contradiction arguments. Let's say it's divided by some, well, I would just say there exists a continuous mapping. The ball with radius 1 to the boundary of the ball radius 1, and the, let's say, T. So negative T does not have fixed point. And this contradiction. So this will gives you the fact that, okay, so there must be exist one such that the ball, they are in the ball all the time, and if they are in the ball all the time, then this will gives you the assumption that the unstable mode is also controlled. So that's the whole story of the compressible Euler. Any question? I have other parts. Oh, sorry, I just want to ask the question about compressible Euler because we have the Navier-Stokes and Schrödinger. Yeah. Okay. No. Okay, so if no, then we are keep on going to the Navier-Stokes and Schrödinger parts. Let's erase all that because we probably will just need these parts. So the major issue to deal with the Navier-Stokes and Schrödinger is to guarantee two things. The first thing is just scaling. You want to make sure the extra term has a exponential decay rather than the exponential growth. And the second thing is to control the derivative loss. You really don't want to close the, especially in the highest order estimate, you don't want to have something that is eventually have the k+1 derivative, and that will be pretty bad. So let's first consider Navier-Stokes because that's easier. And so we're not write on the compressible Euler terms in details because we're not going to use that anymore. So you have extra term will look like this, and partial S is just the compressible Euler terms. So as we mentioned, the first thing is to make sure this delta dissipation should be positive. The alpha, the small r is the blob rate. So this will actually lead to a constraint on the gamma. So if you want to do the Navier-Stokes, all the implosion results only works for gamma is less than that. This is same as the issue in the Schrodinger when the dimension must be greater than or equal to 5, because if you remember, there's a limit of the r star, and the limit should not exceed this the small r should less than the r star, and then this will lead to the fact that this gamma will be less than that. It's a constraint. So if you want to do gamma other than that, you have to get other profiles or other scaling. But for this range, if formally we can treat it as a perturbation, these extra terms, the only difference, as you can see here, will be controlled in this estimate 2. Because when we do the either the Navier-Stokes or the Schrodinger equation, this will never be considered in the linearized arguments. The linearized operator will always drop this, and this will only show up in the nonlinear estimates. And for the nonlinear estimate, you have these two things, right? The first thing is just low order derivative, but all the thing here is the interpolation because this will, of course, very small. So this just because e to the negative delta dissipation s will be less than or equal to the e to the negative delta. It's minus, it's not e to the negative. But S naught is very big, so this will give you the smallness, and this is decay. So less than or equal to delta 1 e to the negative. So this automatically a decay. Well, for the boundedness arguments, this is the only difference that it has because it has two derivatives. But for the Navier-Stokes, we just know that the Laplacian has a good sign. So basically, when you do the homogeneous HK argument, this will just be compressible Euler terms plus extra e to the negative delta mu times this. So the highest order term will be the gradient k applied on the Laplace U. The other terms will just be lower order than that. So this will give you a good term because this thing is just negative. Of course, you will have the gradient coming out when this gradient hit on this, but then you will use this good term to absorb that when you have one gradient extra. So this is for the Navier-Stokes. So this will gives you less than some OE. And then if you recall our high order derivative arguments, the OE is always good. So, but for the Schrodinger, things are a little bit more complicated. So let's first write down the Maslach transform and all the Schrodinger equation. But before that, is it clear for the Navier-Stokes? Okay. For the Schrodinger, this is the focusing version. So we mentioned at the beginning that of yesterday that if you use a Maslach transform, it will corresponding to the compressible Euler plus a forcing. So the Maslach transform is this. So if you're plugging in and taking, so every term will have an exponential e to the I phi, but in front of that, you will get a real part and imaginary part. So take the real part, you will get the equation for velocity, and take the imaginary part, you will get the equation for the density. So that's the compressible Euler. So we do the self-similar coordinate change, and still we get the capital U and capital S. Let's don't bother to write down the terms. Consider the compressible Euler. Let's do the extra Schrodinger terms. So what do we have is this. So P is our S21 over R. And the partial S is compressible. So the same issue happens that this part is same as the Navier-Stokes because you have a coefficient, and this coefficient should be positive or negative. So first, for -2R should be less than 0, so R is less than 2. And this gives you dimension should be greater than or equal to 5. And there's also some related constraint of the nonlinearity. So basically, the higher dimension, the higher nonlinearity, the much easier you can get the R greater than 2. That's how it works. And then the second, the derivative loss. So the derivative loss cannot be controlled directly by this bootstrap argument. So basically, the highest energy should be changed to another energy. And so first, let's do the coordinate or the variable change. So what we are going to define is the logarithm density. So W is 1/2 of log P. So what does this gives you? This gives you P is equal to e to the 2W, and S is equal to 2e to the 2w times alpha. So now we want to derive the equation for w. And then we do the time derivative on both sides. So partial S is e to the 2w alpha times 2 alpha partial SW. And also you have the gradient S is e to the 2w alpha, 2 alpha gradient W. So what is the equation for W? Partial SW is just the 2 alpha S partial SS. So plug in the equation for L. I have to write down the equation for S again. Sorry. Oh, I'm out of battery. That's very bad. I have to remember what I wrote. But hopefully I can. Okay, so this is the gradient S minus alpha S divergence U. So this is the equation for S. Then you have the partial S over S is just S over S. Did I miss the term? Yes, I did miss the term. This one. Okay. So the partial SW is just this. The negative y plus u dot 2 alpha gradient W. Let's see. This part is gradient W minus 1/2 divergence U minus R minus 1. So this should be the equation for partial SW because you are divided by 2 alpha again. And then you have the quadratic term, linear term, and the constant term, right? Okay. So, yeah, sure.
I have one here.
Oh, thank you. I think probably I can use my computer. Here. So now instead of having 2 equations, you are actually having 3 equations. Just to, of course, it's artificial 3 equations. Let's see what we get. I want to erase this part. So I will still don't write down all the compressible Euler terms, just leaves the Schrodinger terms there. So partial SU is compressible Euler plus e to the 4 minus 2rs. Oh, I forgot to write. This gradient of Laplace square root of p divided by square root of p. So what is this? So the square root of p is s to the 1 over alpha, 2 alpha. And we know that s to the 1 over 2 alpha is w. So you have the e to the w divided by e to the w. And then this gives you gradient e to the w, gradient w, e to the w. So this is gradient Laplace w plus the gradient w squared. So it's a linear plus quadratic when you write down it in the exponential w term. So this will leave gradient Laplace w plus gradient w squared. So this is the first part. And the partial SS is just compressible Euler. And partial SW, this is what we want, is negative y plus u dot gradient w minus 1/2 divergence u minus r minus 1 over 2r. So those are the extra terms, and the goal is to use these extra terms to eliminate all those higher order terms in here. So the energy is this following. So EK now is not the homogeneous HK norm, is this one still plus this one, but we will have a 2 e to the 4 minus 2 rs gradient k plus 1 w 2 square. So that's the thing that will eliminate all the things. So let's see how it works. So partial S EK still are compressible Euler terms. Plus some bounded term. For example, derivative heat here, it will be bounded. So I will not write down details. But the real terms that matters are those. For example, we have, let's divide it by 2. The gradient Ku e to the 4 minus 2 rs Laplace w, a gradient, Laplace w plus gradient w squared. So this is term that matters because it's coming from the equation of u. And then the second term matters, of course, is our new equation, this w equation. So this gives you e to 2 s gradient k plus 1 w. So now I will only write down the major terms, which are the terms with high derivative. So one major term is one k plus 1 derivative hit on here, and another is k plus 1 derivative hit on u, because gradient k plus 1 u is still high order. Here is only gradient k u. So I will write down everything, and this will be, let's say, gradient k u dot gradient w minus gradient u, gradient k plus 1 w. Of course, the most important term is this one, so it's divergence. Gradient, oh, this is 2, k plus 2, k plus 1, w. Minus, and there's here. Okay. So let's get the cancellation. So first, this one is just integration by parts. So this one is automatically gone, plus OEK. And what about the other ones? Do I have a 2 or something? I think 2 is here. And because here is times 2, so this is, there's also a 2. Let's see. I think I forget weight. So the weight is very crucial, as you will see later. You will put e to the 2w weight. So this is also the p. E to the 2w is equal to p. Because if there's no weights, there's no cancellation. So I will write down it as S2L2P. L2P. So now I will write left thing down. So let's first consider the term 1. So term 1 is this. Plus gradient K W plus the 2 gradient K plus 1 W grade and the gradient W plus e to the 2W plus lower term. So let's say OEK. And then you can perform the integration by parts. So this has 2 derivatives. You put 1 derivative in the gradient K, and 1 derivative should hit on e to the 2W, and this will cancel with the second term. So this is negative gradient K plus 1U plus 2. So this is the same term that we just wrote it down times e to the 2W. But there's the other terms when the gradient is hit on this. So it's negative 2 gradient K and e to the 2W, 2 gradient W. This is exactly the second term. So what you get is the first term left. Okay, imagine if it's not this e to the 2W weights, there's no cancellation, and then you will have bad things happening because, oh, sorry, this is times gradient K. So this is the first part, and we'll have the second part. The second part is just coming from the term of W, and it will give the exact cancellation as you will see. So this is term 2. The term 2 is this. W. Negative divergence. Oh, sorry, this is U. So how do you control this part? So this, you still use the integration by parts, right? You put this divergence into here, and then e to the 2W will give you a term cancel this part. So this gives you e to the two. To the blue and plus. And to the blue. Oh, this is plus 1. 2. And these two are cancelled, so you are left with this positive term. And then those is cancelled with E2. And then these two are cancelled with each other, and you will have a bond that is fully compressible Euler plus lower order term. Well, of course, you have some decay coming from it, but the idea is compressible Euler. And the same thing can be done to show that this is bounded as well. Okay. So basically, this weight will deal with anything. Oh, we still have some time, so I will talk a little bit about how to do the torus, because we all talk about whole space but no torus. Well, the torus is actually very cute and easy. Well, at the beginning we thought it would be very complicated, but actually it is not. And this thing is really characterized by the behavior near the blow-up points. So we can see this from the following fact. So now instead of perturbation, instead of do the perturbation near the self-similar solution, you do a cutoff, because now the self-similar solution is defined on the whole space. But on the torus, the radially symmetric self-similar solution doesn't fit. So first, in self-similar coordinates, the space variable, if you are originally in the torus, it is actually in the e to the s torus. It's in an expanding torus because you are shrinking your coordinates. And then from this expanding torus, what you are going to do is the following things. So the perturbation is actually, or the solution is actually perturbation plus a cutoff e to the negative. And same for the s. Well, for technical issue, you probably want to get a different cutoff because you don't want the density to be 0. But the idea is the cutoff is a fixed cutoff in the physical space, but it's expanding cutoff in the self-similar coordinate space. And then all the estimates are should follows, except you have extra terms. And partial s. And this, well, I write EU tilde and ES tilde, but they don't really depend on U tilde and S tilde. They are just the terms coming from the errors coming from the fact that you plug in this into the equation, it is not a stationary solution. But you'll figure out that when you plug in such kind of things, no matter how the weight you choose, well, you will always have this e to the negative s coming out because the derivative will hit on that. So both this and this, let's say we bounded in some space, no matter which space actually, this will be less than or equal to e to the negative s times s. And as long as S0 is very large, this will give you very small things, and it will just add to all the estimates that you get for the compressible Euler. And this is for the torus case. So this really, of course, there will be some boundary terms in integration by parts, but they were all canceled, and that's how it works. Okay. So I think that's what I want to say. Thank you. Mm-hmm. Yes.
So you have a cutoff just because